Hello everyone, this is Mr. Rothkeb here for your Gateway number 5 instructional video. So let's look at adding versus multiplying monomials. When you talk about a monomial, first of all, mono, the prefix mono means one, and meal is basically, as opposed to a polynomial, is basically one term. What it's called to. So if I had 3n plus 5n, that is two terms. Because 3n is one term. And the little bit more of the anatomy here, these are both called coefficients. This is the numerical coefficient. Good. And this here, maybe I'll make a red arrow, there we go, is the algebraic coefficient. And so the thing to realize is that every coefficient has an exponent. So if I wanted to just get crazy and write this as 3 to the first power times n to the first power, I could do that. You will rarely ever see it written that way, but I could if I wanted. And that's important to remember because you want to remember that every number has an exponent. Every coefficient, rather, has an exponent. If it's not written, that just means it's to the first power. In addition to that, I can also think of this as, because this is one term, addition separates terms. So don't think of it. There's a couple other things later on in math that might separate a term, but for now, to keep it simple, multiplication does not separate terms. Addition separates terms. So if I were to write some crazy term like 2 times 7 times n to the second times p to the third times z to the seventh, that's all one term. As long and as crazy as that looks. So you want to keep that in mind, because when you are adding versus multiplying monomials, you are still doing GEMA from last time. So you're still doing groupings, exponents, multiplication, addition, just like we did in Gateways number 4, and to a little bit in Gateway 2 and some of 3. So let's take a look at some of these. So let's look here. Now, if you want to expand these out, you could expand this. Well, you could put 1 times 5. It's always times 1. But for now, if we wanted to get really crazy and write 5 times b times 4 times b times b, you could do that. And once again, if you want to get super crazy and put an exponent of 1 on each, you get nuts and do that. Now, is this necessary? No, of course not. But I think the big thing I see with a lot of people is they forget. A lot of students get simple ones like this incorrect because they forget that right here, this is b to the first power. So what that means is, and the reason I write it like this isn't to confuse you or make you do a bunch of extra work. It's to think about, okay, wait a minute. This, we need to simplify into one term. So if we have 5 to the first and times 4 to the first, we can, and I'm going to do something that also is not necessary every time, but we can separate this into, if I were to rewrite what I wrote above in order, then we'd have this. So 5 to the first times 4 to the first, well, that's just good old-fashioned 5 times 4. And then b times b times b. Well, if this was any number, if it was 3 times 3 times 3, or 4 times 4 times 4, or 5 times 5 times 5, whatever it would be that number to the third power. So we would write times b to the third power. And then once we get multiplied, because it's multiplying, and we're multiplying a numeric times an algebraic coefficient, this multiplication symbol in the middle isn't necessary anymore either. So more commonly, you'll see it written like that. Now, if you're saying, wait a minute, the first question students always ask is, do I have to show all this work? I think you're missing the point. The reason that I show you this is to illustrate why you're going from here down to here. So if you ever get stuck, so can you, I bet there's a lot of you out here could probably just do this in your head, and that's great. But if you ever get stuck, think of this stuff here in the middle. This is the why of why you can go from this expression up here to the one down here. This is the why of what you can do. So if you scoot over, let's see what we can do here. Here, we wrote some notes over here, so I'm just going to scoot this one over. So 3k to the second times 5. Okay? So once again, if I wanted to get crazy and expand it, this is called expanding, by the way. And there's ways to further expand if these were not prime numbers, but we'll get to that later. So, and then rewrite it. Okay, and we can say, well, 3 times 5, that's just good old-fashioned 15. And then k times k times k to the first, k to the first, and k to the first, and k to the first is going to be k to the third. If it was any other number, if this was 3 times 3 times 3 times 3, or 4 times 4 times 4, or 5 times 5 times 5, or whatever it was, it would just be to the third power. Cool? Now let's go down if we have something that isn't to the first power. Let's just skip down here to 4. Once again, the things I was showing you before, the rewriting it, or the expanding it rather, not necessary. You're going to get good enough at these where this is so not necessary. But if you ever get stuck, anything dealing with exponents, rules of exponents, if it ever gets more complicated, think of this in your head. Or if you want, literally write it down. Because this is what's actually happening. Also gets kind of annoying, so there's a lot of writing here. This is what's actually happening. So in my mind, when I see this, I count, I'm thinking, oh, there's 5 x's, so that's going to all become x to the 5th. And then if we have 6 to the first times 5 to the first, that's just going to be good old-fashioned 6 times 5, which is 30. Here, sorry, hang on. How about we write it like this? First, and then 30x to the 5th. Now, is it, once again, you can go straight from this step straight down to here. Totally fine. As a matter of fact, that's desired once you get good. There's no sense in writing all of this if you fully understand it. The reason I bother to write it is because it shows you the why these things are the way they are. All right, let's jog over to the next page here. Let's get into some situations where, here's a good one. So we have m times 2m. So with every monomial, so this is a monomial times another monomial, which is just going to give us another monomial. So if we want to multiply, we have to, every single monomial has to have a numeric, and an algebraic. Although there's some theory that says not. For our purposes now, every one of them is going to have a numeric and an algebraic coefficient. If it's just like a number, it may not have the algebraic, although you could argue it's the 0th power. Not important. But basically, what you should be thinking of this as is 1m. So get in that good habit of just writing 1 times m, because that's really what it is. So if I wanted to expand this out and do all that extra work, times 2 to the first times m to the first, we would now multiply and then rewrite it. Good. And then it would be 1 times 2, of course, is 2. M times m to the first times m to the first. Any of those numbers, 3 or 4 or whatever, would be to the 2nd power. And then we would just write 2m to the 2nd. Good. Let's move down to some of the ones that have multiplying here. This one is no different. Let's not write it all out because I don't feel like writing it. But in essence, let's skip a step. Let's write it as 5 times 3 times 3 times m to the third times m to the second times m to the third. Rewrite them in order. And if I really want to write them all out, I really don't. But if I did, it'd be 1, 2, 3. It'd be 1, 2, 3, 4, 5, 6, 7, 8 m's. And then 5 times 3 times 3 is what, 45? Okay, so it'd be 45, sorry for the sloppy writing, m to the 8th. Okay, so does it matter what order you write them in? No. Does it necessary to even write all of this stuff out? It's not necessary, but if you ever get totally stuck, think of it that way. Think of how many m's you have. Students get way over confused because they think of it as like, is this the thing where you like add the exponents versus multiply the exponents? Don't think so much. It's just, if you were to put a number in here for m, whatever it would be, 3, 4, 13, whatever, it would be 1, 2, 3, 4, 5, 6, 7, 8 to the 8th power, number of m's. Skip down here to adding. For now, adding is going to be different. So if I were to, first of all, let's remember our good habit from above, which is what is the numerical coefficient of this monomial? Whoops, that's maybe not erased what I was writing. There we go. 1. So it's 1n plus 4 plus 4n. What is the algebraic coefficient of this? Well, later on you could learn that you could make the argument, I suppose, is n to the 0th. For now, don't worry about that. For now, just realize that it doesn't have an algebraic coefficient, so it's just a number. 1 times 4, or just 4, it's 4. So the reality is that if I were to input a number here, let's make up a number. Let's put 1 times our favorite number, minus 7. I'm going to put 7 here. So if you were thinking, well, wait a minute, it's just 1 plus 4 plus 4 is going to be 9n, right? Yay. Well, let's see here. Let's see if that actually works out. If I put 9 times 7, 63, let's see what we get here. So we have 1 times 7 is 7, plus 4 times 7 is 28. What is that going to be, 32, 39? Pretty sure that's right. Good, wait, 35, yeah, 39. Good. As you can clearly see, they're not the same thing. That's why this is not how you add these things. If you think about it, we are not multiplying anything times 7 here, which is why this is not a like term. So these two and these two are what we refer to as like terms. Like terms. And what that means is that because we can say, wait a minute, 1 times 7 plus 4 times 7, that's going to be 7 plus 28. Well, 28 plus 7 is 35. That's the same thing as 5 times 7. So if we were to add these two things, and we were to say, look, wait a minute, 1 times 7 plus 4 times 7, or anything really, is the same as 5 times that thing. So if we were to input 7, there we go. We get 7 plus 20, good Lord, come on. 28, there it goes, times 35. Those are the same thing. That's why those are like terms, is because anytime you have this, 1 times something plus 4 times something is the same thing as 5 times something. So long story short, we can add those together. Instead of saying 1 times 7 plus 4 times 7, we don't know if it's 7. We just made that up. So we're not going to write that. We're going to say 1n plus 4n is the same thing as 5n. So going back up to our question, we know that these are now like terms. So that's going to be 5n. But we just said that green 4, well, that's not the same thing because we're not multiplying it by some number. So we just have to let it be. So basically the simplification of this is going to be that 5n plus 4. And that's it. Good. is here. So once again, there's a lot going on here. This explains the why. As you get good, you'll be able to skip the blue, you'll follow the path of the blue arrow and just be able to go straight down to simplifying this expression. But that is the why of why we do it. The reason I bother to explain that is so many students don't think of the why, and then they get really confused on why certain things exist. All right, let's try one more maybe from the other. Let's try a couple here. Ooh, I like that one. Let's do 26. Yeah, let's do 26. And then maybe one more and we'll call it a day. All right. If you remember all the way back for the not only Gateway 2, but Gateway 4, the big thing we were talking about is keep, change. So how many terms do I have here? If you said 4, good for you. There are 4 terms. Let's use salmon. So 1, 2, 3. Here, let's use, there we go. Let's use like terms. There we go. 3 and 4. The operations are here. So if you're saying to yourself, wait a minute, I thought that was subtraction, you're not wrong. Let's think of it instead as just this here. But what that means is if you're like, wait a minute, we have to keep, change, you're absolutely correct. So we need to keep, change. Let's see if we, keep, change. And we don't need to keep, change here because there's addition. You only need to keep, change if there is subtraction. And just like in Gateways 2 and 4, let's rewrite everything we got here. Let's make it nice and pretty the way we want it, not the way the typewriter types it out. Okay. So, if you remember from what the question we just did, the ones that are in peach here are like terms. So 1 and 1 are like terms, and also negative 3k and negative 8k are also like terms. So if you remember from what we did the last question too, negative 3k and negative 8k, well, that'd be the same thing as if you had those negative 11 times k. So that will end up being here as negative 11 times k. And then these here, 1 plus 1 is obviously 2. So these would end up being, I don't know if I want to write it this way too. So a better way to write it, if you wanted to even rearrange it, although you do not have to do this, I'm just showing you for the sake of completeness. Good. We would have negative 11k plus 2. Is it okay to write 2 plus 11, negative 11k? Absolutely. Either one of these are completely, perfectly correct. You'll often see in typewriters you write the letter term, the algebraic term to the left. Honestly, it's not something you need to worry about. Let's skip to one last one that I promised. Let's go to one more multiplication one. Yeah, number 35. So back to multiplication. So I'm going to ask you how many terms, or in class I would ask you, how many terms do you see here? If you said 2, be careful. Go back to where we said at the start. There is actually just one term. Because what separates terms? Addition. So there is only one term. It's one big whole thing. So all we have to do is just multiply everything together and get everything squished together more, simplified. So we can do what I did before, where it's 3 to the first times y 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 to the first, blah, 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 blah. But that takes a long time. So we could rearrange again, 3 to the first times 6 to the first times x to the fourth times y to the fifth times y to the fifth. We could do that. And remember, we'd have 18 times x to the fourth. Now, can we multiply any of these together? Well, let's think about it. If we were to expand this one, I didn't want to expand the one above it, but let's expand these in order. Let's make this 18, straightforward. This is x times x times x times x times y times y times y times y. I said I didn't want to write it all the way out. Well, I guess I'm just gonna. And I'm gonna run out of room. So if you think about it, this is what we really have. Do you have to write it this way every time? Please don't. But we notice, wait a minute, there's 4, that's going to be x to the 4th, and there's going to be 10 y's here, so it's going to be y to the 10th. So a common mistake I see people make is they think that they need to add, somehow get everything, all this together, and do something like 18 xy to the 14th or something. I think they just say, hey, there's going to be 14 of these things. Great. And no, that's not at all what we want, because you're just counting. You're literally just counting. How many x's do we have? 4, x to the 4th. How many y's do we have? Well, 10, y to the 10th. So that's why this here is your winner. Hope this helps. As always, with any questions, post them on Google Classroom, and we can respond to you as soon as